what I'm going to do next is I want to add another router here in my AS600. So this is going to be the network that I will be running now. So let's do that magic again. So this one goes away, thank you very much. So I want to add R5, and R5 is also going to be in AS600, and I want R5 to have the peering only with R2 using loopback interfaces. So no peering allowed between R5 and R6, just direct peering between R5 and R2, no other peering allowed. So same as before, same as it was the case between R6 and R2, I already have my OSPF pre-configured for this, and all I have to do is just do no shutdown on that interface. So let me bring R5, and I'm going to move it here to the back. And on R2, I'm going to say interface 0010.205, no shutdown. So when it comes back up, if I do show IP route OSPF, here I should be having the route for R2, and from R2, if I do show IP route OSPF, I should be able to ping R5. So this is good. So far, so good. Let me bring in my notepad, which should be somewhere around here. There it is. So this one here was temporary. I'll get rid of it. So this is the configuration that I had so far. And you know what? This is pretty much what I need now. So this is going to be the configuration on R5. So this goes in because I'm peering with R2. And on R2, what I need right now is just to change these to 5s, like so. And I should have the peering between R2 and R5 ongoing. So if I do show IP BGP summary, let's give it a second. Unless I made a terrible, terrible mistake here somewhere. No, there it is. So if I do show IP BGP summary, I see that I have the peering and that I'm receiving some routes. Now, the task is simple as it was before. What I want to do now is have ping between R5 and R9 going. Again, no redistribution, no new interfaces allowed, and no new protocols allowed. So I already know that R2 and R9 can ping each other. So what I'm going to do now is I'm simply going to add the network statement on R5, and let's see if this actually solves my problem. So I'm going to go to R5, and I'm going to say router BGP 600, address family IPv4, network 192.168.0.5, mask, and I'm going to advertise this. So if I do show IP BGP summary, so show IP BGP, what I'm going to be seeing here is that R5 is now here. And if I do show IP BGP neighbor to advertised routes, I'm seeing that I'm actually advertising this to R2. Now, if I go to R9 and if I do show IP BGP, this is what I'm seeing. I'm getting the route from R2, and I have my own local route. If I go to R6, show IP BGP, I'm getting the route from R2 and from R9, but where is R5 route? If I go to R2, show IP BGP, I'm getting the route from R2 and from R9, and here is the one from R5. If I go to R5, if I do show IP BGP, I'm getting the route from R2 and R5, but where is the R9's route? Well, this is where we hit one of the most important rules of iBGP peering. And that's the rule of, as I like to call it, iBGP split horizon. So iBGP split horizon is the rule that says route received from an internal peer will not be advertised to other internal peers. So this is a loop prevention mechanism inside the autonomous system. So inside the AS, this is the loop prevention mechanism. So what we have here now is R5 connected to R2, connected to R6, which is connected to R9. Now, when R9 advertised the route to R6, this was an external route. Now, when R6 advertised the route to R2, this was an internal route. And R2 will not advertise an internal route to an internal peer. Now, you might be now looking at the screen unusually and saying, hey, but hold on, wasn't this route an external route? Well, yes, it was, but the internal or external route has nothing to do where the route originated. It simply means where are we learning it from. Let me show you that. So if I go back to the terminal, here I am on R6 now. If I do show IPBGP, this is the route from R9. Take a look at this empty space here. This empty space here tells me that this is an external route. Why? Because let's compare it to the route from R2. R2 has this tiny little I here, which basically says this is an internal route. So on R6, the route from R9 is considered to be external. Route received from external peers will be advertised to internal peers. So if I go to R2, and if I take a look at the route for R9, take a look at this. Now we do have an I. Why? Because this was learned from R6, and this is now an internal route. So we are receiving the route from an internal peer. That means that we are not going to be advertising it to another internal peer. So this is the rule. Now, to work around this rule, to provide the connectivity inside the AS, usually what we are going to have is the direct peering or indirect peering between R5 and R6 so that we can have a full mesh. So full mesh requirement inside an AS is actually a workaround for this split horizon rule. So if everyone is peering with everyone, we don't care about the split horizon rule because we are going to get the routes where they need to go. But we are restricted from doing that. And besides, you know what the problem with the full mesh is? We already talked about it. It's n times n minus 1 over 2, the number of peerings that we might need to maintain. Now, in our case, this is pointlessly small number, but what if we had 500 routers in our network, or 5,000 or 50,000 routers in our network? In that case, this number of peerings to maintain the full mesh becomes a significantly large number. So to work around this, there is a solution, which is to employ something called the route reflectors. Now, route reflectors are internal peers that are specially configured to allow the reflection of internal routes. Reflection of internal routes simply means that we are going to relax the split horizon rule, and we are going to allow an internal route, under certain circumstances, to be advertised to other internal peers. So these are the rules of route reflection. To examine them, I'm going to run the network, or actually not run the network, but I'm going to use this as an example to explain it. And in this network, these are going to be the routers. So this here is, let's say, AS100, and these are here some other autonomous systems. So from the perspective of the router that will be configured as our route reflector, this is what we are going to have. Now, all peering sessions in my network are going to follow the black lines. So there are not going to be any other peering sessions, just those that follow these black lines that I drew. So let me clean this up just a little bit. So this is our route reflector. So let's say that this is external peer 1, external peer 2, external peer 3, and external peer 4. Now, from the perspective of route reflector, we are going to configure these two routers here as clients. So this is going to be client number 1, and this is going to be client number 2. Now, these two routers here are going to be just regular IBGP peers of our route reflector. And in route reflector terminology, these are called non-clients. So I'm going to call them NC1 and NC2. Now, let's see what happens on the route reflector when the route reflector receives the route from an external peer. So, external peer sends the route to route reflector. This route will be advertised to external peers. If the route reflector has external peers, it will also be advertised to non-clients. Oh, oops, sorry, this is the client. Let's say, yes, it will be advertised to clients. And just for completeness, this will go out this way. This route will also be advertised to non-clients, so this goes here, and this goes here. Now, because non-clients are regular IBGP peers, and this at this point is an internal route, these two are not going to be advertising this route to each other. Now, let's take a look at what happens with non-client routes. So let's say that we received the route from a non-client. So there was this route that was sent here, non-client will be advertising it here. Because these two are just regular IBGP peers, non-client 2 will not be advertising this here, but this router here will be advertising it. So this route will now be advertised to external peers and will be advertised to clients. So this goes out here and this goes out here. But it will not be advertised to non-clients because these two, non-client 2 and route reflector, are just regular IBGP peers. Now, let's see what happens when we receive the route from a client. So let's say that the client here receives the route. This route will be advertised to the route reflector, and this will be sent to external peers. This route will also be advertised to other clients and will also be advertised to non-clients. So this goes out here and this goes out here. These two are not going to be advertising this route to each other, and this goes out here. So these are the basic rules of route reflection. So what we need in our network right now is to declare one of our three internal routers, either R5, R2, or R6 as the route reflector, and one of them needs to be a client. Now, the best choice for the route reflector here would be R2 to be the route reflector. Now, one of these routers, R5 or R6, needs to be the client. It can be either one or both of them, but at least one of them needs to be the client. Why? Because if we take a look at these rules, if one of them is the client, so let's take a look at this network here. So this is pretty much what we have. So ignore non-client 2 and ignore client 2. This is R5, R2, R6. This is R9. So if we receive the route from R9, and this is R6, if you advertise it to route reflector, and this is a non-client, we are going to reflect the route from client to a non-client. Now, let's say that the situation was the other way around, that this is R9, this is R6, and this is R5. If we receive the route on R6, this is a non-client, it will be advertising the route to route reflector, but the route received from a non-client will be advertised to a client, which is fine. Now, let's take a look at this scenario here. Let's say that this is R9, this is R6, R2, and R5. If you receive the route here, this is an external route, it will be advertised to route reflector. It is received from a client and it will be reflected to the client. So either one of these solutions is the correct one. But, you know, better safe than sorry. Let's declare both of these routers to be our clients. So this is what I'm going to do. I'm going to go to R2 and I'm now going to configure it to be the route reflector for R5 and R6. So to do that, I'm going to enlist the help of my notepad. So what I'm going to do here is router BGP 600 address family IPv4. Again, this is a policy command because it changes the behavior of the routes. Are we going to advertise the routes or not advertise the routes? And then I'm going to say neighbor 192.168.0.5 route reflector client, and I'm going to do the same thing for R6. So this goes in on R2. When I paste it in, the neighbors are actually going to reset. When they come up, if I go to R5, if I do show IPBGP, at this point I should be seeing the route from R2, from R5, and from R9. On R6, if I do show IPBGP, I should be seeing the route from R2, and from R5, and from R9. On R9, if I do show IPBGP, of course, there we go. On R9, I should be seeing the routes from R2 and R5. So at this point here, I should be able to ping from R9 to R5. From R5, I should be able to ping R9. So this is how we can use route reflectors to actually scale the peerings in our autonomous systems. Route reflectors are just one way of scaling the peering in our autonomous systems. Another way that we can scale the peering in our autonomous systems is to use something called confederations. Now, to explore that, I'm going to again expand our network a little bit. So let me create a copy of this. So to expand our network, I'm going to add one more router to the mix, and this is going to be our R4. Again, let me do my magic. So this needs to go all the way to the back, and this one here gets deleted. So what I'm going to do now is I'm going to add R4 to the mix, and R4 is going to be in AS400. Now AS400 and AS600 are going to be together in AS2456. Now OSPF is only going to be running on R5, R2, and R6. So OSPF is only running in AS600. So let me just make sure that that is somehow visible here. In AS2456, between R5 and R4, I'm not going to be running any OSPF. So it is going to be just the peering between direct sessions here. So now this illustrates one more thing. This illustrates the value of actually reading ahead in the lab. If you have known these tasks, if you have known that this task is coming up ahead, you would have not created this peering between R6 and R9 in such a way that R9 actually peers with AS600, because R9 now actually needs to peer with AS2456, because AS900 is not part of our confederation. But anyways, we're going to change that when the time comes. Let's bring this peering up and let's get our confederation going. So what I'm going to do here is, again, I am going to need my notepad. Let me see just, yep, I have that configuration. So I'm going to go to R5, or actually first let me bring R4 to the mix. And again, the only thing that I have to do here is interface serial 010.504, now shutdown, show IP route connected. What I should be able to do is ping R4. There we go, that worked. And let's try from R4 just for to make sure that we have communication in both directions. We do. So bringing in my notepad here, I'm going to start from R6, oh, actually from R5. There is one thing here that I need to add, which is going to be BGP confederation peer is going to be 400. And what I need to add is BGP confederation identifier. Actually, it's 400 here. And the confederation identifier is 2456. So this is what I need to add on my R5. And actually, this is what I will need to add on R5, R2, and R6. So let me just add it here. Oops. Just going to add it here. Going to add it here. Going to add it here. The peering is going to be between directly connected interfaces. So I don't need update source. So 45.4, 45.4. So this goes on R5. And on R4, the configuration here is 400. This changes to 600. Aha, just one second, I think I made a mistake. There was a typo there, so let's fix that. So this is 5, 5, and 5. So now this goes to R4. So right now, I should have the peering come up, and I do have it up and running. So this peering between directly connected interfaces between 4 and 5 is now up and running. But this is not an external peering, this is not an internal peering, this is actually a confederation peering. So this is CBGP peering going on here. So let's see if on R4 I actually have any routes. Before I do that, let me just advertise the loopback of R4 into the BGP. So I'm going to say router BGP 400, address family IPv4, network 192.168.0.4 mask. So this is what I'm going to do. Now, if I go to R5 and if I do show IPBGP, I'm going to see R4's loopback. And take a look at the AS path here. Now, this AS path here with 400 in parentheses is actually telling me that this is coming from a confederation peer. This is not an internal session, this is not an external session, this is coming from a confederation peer. Now, if I go to R4, if I take a look at show IPBGP summary here, or show IPBGP, I'm going to see that I am in a little bit of a trouble. Now, the little bit of a trouble that I'm in here is that R2 and R9's routes are not reachable. Take a look at the next hops for those routes. They are unchanged. So even though this peering here may have certain characteristics of external peering in a sense that we would still by default need to be directly connected to get this working, what I'm having here is that the next hop is unchanged, just like inside the autonomous system. So even here between these two confederation members, I need to do something extra. So I'm going to do the same thing that I did here on this peering. What I'm going to do here is I'm going to say next hop self in this direction, and I'm going to do next hop self in this direction as well. So let's go back to my terminal, and on R5, I'm going to say router BGP 600. I'm going to say address family IPv4. I'm going to find that neighbor statement. There it is. And I'm going to say next hop self. Oops. One space is needed there. And on R4, router BGP 400, address family IPv4, neighbor, next hop self. So now if I do show IPBGP, now I will see that I actually do have the reachability here. So I do have the route for R9, and here on R9, actually let's take a look at R6 first. If I do show IPBGP on R6, I see now, okay, maybe, okay, there is one more thing I need to do. Apologies. On the session between R5 and R2, I also need to do next hop self, because let's take a look at R2. If I go to R2, if I do show IPBGP, I have the exact same problem. So I can see here that I have R4's loopback with the next hop of the address that is not in my routing table. So in order to fix this, I need to go to R5, and on that session, so that would be neighbor 192.168.0.2, next hop self. So now I'm going to see that I do have a difference in behavior. So if I go to R6 here, I will see that I actually do have R4's prefix. So from R6, I should be able to ping R4. Well, with the source of loopback 0. I should be able to. Oh no, sorry, not from R6, because R6 is not, of course, advertising its prefix. But that route is at least present on R6. But now I have a bigger problem. Take a look at this error message. This error message is telling me that I have a peering problem. The peering problem from R9, because now R9 thinks it's peering with the wrong autonomous system. This is something that I need to fix on R9. And there is, fortunately, a very easy fix for that. So I'm going to say show run pipe section router BGP. Going to go in here, and I'm going to change this to 2456. And now the peering should come back up. If I do show IPBGP summary, oh come on. Brute force sometimes works the best. There we go. So if I do show IPBGP, these are the routes that I'm receiving on R6. And if I go to R9, show IPBGP, these are the routes that I'm receiving on R9. So from R4, I should be able to ping R9. But I want to show you something. If I go to R6, so here I am on R6, take a look at the AS path for 192.168.04. The AS path for 192.168.04 is showing me 400 in parentheses. This is what I learned before, means that it is coming from the confederation peer. But if I go to R9, if I do the same command here, take a look. That whole confederation is now hidden from me. So this is how you configure the confederation peers. One question that I got asked, so did I have to remove the route reflector configuration from R2 to make this work? Well, no, because route reflectors and confederations are not really mutually exclusive things. They sometimes work hand in hand together, and it's important to know when you can use one and when you can use other, or I should say when you should use one and when you should use the other. So let's say here that internal peering scaling. So this is just going to be a quick guideline for the scaling of internal peerings. So we have two options here. One is to use the route reflectors and the other one is to use confederations. Now, when you can use route reflectors and when you should use route reflectors, the answer is very simple, always. You can always use route reflectors. They are a very, very good everyday solution. And they have very few negative sides. Now, confederations, in my opinion, are always a special case. In real life, these would be things like mergers, acquisitions, divided control. By that I mean that you might have parts of your organization that are controlled by another group, and let's say in another country, and you want to present the global view of your autonomous system to the rest of the world, but you know that internally there are different policies in that part in the network than in some other part of the network. And in that case, the confederations may make sense. But inside this confederation, to scale the confederation itself, you might need to use the route reflector, because if we take a look at how an autonomous system might look like, is let's say that we have these routers here, and these belong to one confederation member, and let's say that these are the routers that belong to another confederation member, and this is a confederation. So if you peer between these confederations, let's say between these two routers, how are you going to peer inside this confederation? Well, one of the things that makes sense is to have some peering that, for example, looks like this. So that you have these two, for example, as route reflectors, or in this case here as well, you might want to do something like this. So that these two are route reflector. So inside a confederation member, to scale this peering, to scale the peering inside the confederation member, you might want to use route reflector. So they're not actually mutually exclusive, but to scale the whole thing and to have some sort of separate control between this member here and this member here, you might want to divide your large autonomous system into smaller, more independent BGP routing units, so to call them. So this is what confederations do. Now, for the purposes of the lab, you should use route reflectors every time when something looks like hub and spoke. Now, what I mean by when something looks like hub and spoke. Now, let's say that you actually do have hub and spoke environment. So that this is a physical hub, this is a spoke, this is a spoke. And let's say that this is running frame relay. And they tell you, peer between spoke 1 and the hub, peer between hub and spoke 2, and peer between spoke 1 and spoke 2. Now, for the purposes of BGP, this is not actually hub and spoke. This is a full mesh of peerings. But let's say that you had, for example, an Ethernet network in which you had multiple routers connected to your network. And let's say that they are R1, R2, R3, R4, and R5. And the task said, peer all routers with R1, but don't make any other peerings. Now, for the purposes of BGP, this does look like hub and spoke. For the purposes of BGP. Why? Because this router here appears to be the hub of your BGP peerings. In this case, this here needs to be made into a route reflector, and these here need to be clients. Now, the good news is that you don't actually have to configure the clients. The only router that you are actually configuring is the route reflector. But every time something looks like hub and spoke of BGP peerings, so let me clarify that, of BGP peerings, this is when you should use route reflectors in the lab. When you should use confederations? Only when asked. Because they do complicate things, they do complicate the propagation of the next hop, they do complicate, or I actually don't like that word complicated. They introduce complexity. Complicated is not the same thing as complex. Complicated means something that involves a lot of work and involves a lot of thinking. You may or may not get it right. You know, it's fiddly, but that's not what I mean. Complex simply means that it has a lot of moving parts, but once you get all these parts, it's actually a very simple thing. And confederations are a relatively simple thing. They are simply, well, they are actually a complicated thing, but it doesn't matter. Don't go the confederation way unless the lab actually asks you to do that. Now, they might ask that explicitly, and that task may sound something like configure these routers to be in this AS, these routers in this AS, and then put them in a confederation X. That's a very explicit requirement. Or they might say something along the lines, so using our example here, they might say something along the lines of configure routers R2, R5, and R6 in Autonomous System 600, configure R4 in AS400, and make sure that routers 4, 5, 2, and 6 appear to all other routers as AS2456. So this is telling you here that, okay, they between themselves will know the difference between AS600 and AS400, but when the rest of the world sees them, when other routers, like for example our AS900 here, sees them, they are perceiving them as AS2456. In that case, they're actually telling you implicitly that they want you to configure the BGP configuration.